Good evening, everyone. My name is Saida Said. I'm a third year research scholar at IIT Roorkee, and today we will be starting our seventh interactive session. And we will be discussing what we have studied in the sixth week of this course. So, in the sixth week, from the handouts, I could see there are some topics that are on elective resistivity techniques, electrical resistivity techniques. Then there are Wayne shear test, and then we have finalized the paper, the uh, chapter for our subsurface investigations. We have started the retaining walls. So we will be looking at uh, questions on these. And then, if time permits, we will start with a simple question on the retaining walls. Okay, so let's go to the question. A vein shear test was conducted in saturated clay. They're not. Oh, I. One second. Just a second. Uh, is it visible now? Uh, I have shared. Okay, okay. Sorry for the confusion. I forgot to share my screen. Okay, so as I was discussing that we have studied in this week about the electrical resistivity techniques. Uh, okay, so electrical resistivity techniques, Wayne shear test, and the we started initially with the retaining walls. So we will be doing questions on these, and if time permits, then we will move on to retaining walls. So let us go to the first question. A vein shear test was conducted on a saturated clay. You must remember that vein shear test is only like there is a condition for this test that it has to be conducted on saturated soils. One second. I think somebody else joined. Okay. So the height and the diameter of the vein were 101.6 millimeter and 50.8 millimeter respectively. During the test, the maximum torque applied was 30 Newton meter. The clay soil described has a liquid limit of 58 and a plastic limit of 29. See, normally this will be the question for you, the part A only at this level. This will be the only question for you. Estimate the undrained shear strength of the clay from the formula that you have. But I have included these two parts. Why I have included these? Because help you visualize that whatever quantities that you calculate in soil mechanics, we have n number of empirical equations that relate these quantities to some other quantities based on localized tests. It can never be general because of the heterogeneous nature of the soil. So there is a relation that I will be discussing, not discussing, but simply a relation that is being given by Jerome that talks about the corrected undrained shear strength of play for design purposes. Like the CU that we calculate here, there is a theory that we do not use this CU, but we correct it. I'll give that formula. And see here, you can see the relationship between the over consolidation ratio. So it's just the relationship is given to you. You just have to put in the numbers. But the purpose of showing it here is to make you understand that you will find n number of relations between anything that you can calculate in soil mechanics. So these studies have been conducted by researchers. So let us start with this question. Uh, okay, so what is given is, let us visualize by drawing this vein. It has a height of 101.6 mm. It has a dia of 50.8 mm. It will have a, okay. So the torque applied, maximum torque applied is 30 Newton meter. So let's first calculate the undrained shear strength. We know that Cu is equivalent to T over pi d square h by 2 plus d by 6. Because it is not written here that it was half immersed, so let us assume that it was fully immersed and both these surfaces are being used for development of cohesive resistance. So let us calculate. This will be Cu equals into 10 to power 3, let's write in Newton mm, over pi 50.8 square. I've converted the Newton meter to Newton mm here by multiplying with 10 to power 3. So don't get confused. So you will get an answer for this. Cu equals, let's calculate. Are you getting an answer, Vanita? Vanita, are you getting an answer? You're calculating? I mentioned it that it's not written. Let us assume that it's available at both surfaces. I think I mentioned it just 5 minutes ago. Okay. Yeah. Try to calculate and tell me what you are getting. Hmm. Yes. Yeah, that is correct. Ow, excuse me. Okay. So Cu is 0.0624 Newton per mm square. Okay. Let's move on to the second part. What would be the corrected undrained shear strength of the clay for design purposes? So, as I mentioned, that Jerome has given for actual purposes, undrained shear strength value are too high. So it is recommended that they are corrected according to an equation that has been given. Uh, equation, okay. So the equation goes like this. This is most commonly used. Like there are other equations for that also, but the most commonly used equation is the Bejerum's relation. Jerum's relation, not Bejerum, sorry. So lambda equals 1.7 minus 0.54 log of plasticity index. So you see the plasticity index, for plasticity index, the liquid limit and plastic limit have been provided in the question. How much is the liquid limit? This is 1.7 minus 0.54 log of plasticity index, and then our CU corrected. Uh, that is what I'm writing. So the CU that you get from Wien shear test, you have to multiply it by a factor lambda that has been empirically proposed by Jerome in 1972. There are other relations also, but this is one of the most common. And the purpose for me telling you here is that you get, if you convert this into Newton meter, how much will you get? Air, Newton per meter square, kilonewton per meter square. Convert the CU to kilonewton per meter square per meter square. Yeah. So see, this is too high. This is too high for this will be too risky for use in design. If you go like maximum CU we get 50 or something like that, and now if you're using it in design you have to be more conservative. So for design purposes we multiply it by a factor to reduce it. You calculate this factor, it will be less than 1. Calculate this. No, I did not say that. What I'm saying is that usually in actual tests performed by Wien shear test, you get a very high CU value, which may be correct also. It is not that this value is not correct, but when we go for design, we want to be conservative. So we reduce the value that we obtained from the Wien shear test, because Cu will only give strength to the soil. If we assume that the soil is weaker than it is, then we will design our design will be conservative, which means that uh, we will apply lower loads. For example, if you have a CU of 45 and a CU of 65, you may get a design load for this at only 100 kilonewton. That more than 100 kilonewton you cannot apply on this soil. But here you can get about 150, 175 kilonewton. You're understanding the basic principle of design. From design, we calculate the strength of the material, and then we propose that how much load can this material withstand. It is always better to be conservative, but not too conservative. It's always better to be conservative. If from this I obtain a design load of 175 and I put on 175 kilonewton design load on this structure, and it has a more greater probability to fail than this structure, because I have provided a lower load here. Do you understand me? What I'm saying, that it is the design philosophy that we don't want to be we don't want to over predict. This may be an over prediction. This cannot be the exact value, because when you go in field, numbers rarely matter. What matters is that will your structure hold or not. Maybe it is uh, the real strength may be about 58 or something. So we want to reduce it a little because it is too high for design purposes. Do you understand what I'm saying? No, I don't think in your voice. See, what will you do for design? You will have a footing, okay? Then you will apply CNC QU is equivalent to CNC plus, for example, it's a clayey soil. Here C is directly proportional. N will be 9, for example. 9C will be your ultimate load. If you apply 9 into 62 or 9 into 40, you see how the ultimate load will change based on CU. So if you provide a high CU, you will get a high uh, bearing capacity, high final load. So as a designer, I may propose that this footing will withstand 1000 kilonewton when actually it won't. So to be on the safer side, to be conservative, I will reduce this a little bit and then give my design, because even if it is overloaded a bit, it will not fail. It's kind of a factor of safety. Do you understand? Okay. So calculate this. Is the date on of the paper. This is the date of the research. Jerome in 1972 has given this. It is highly unlikely that you will get this in the question paper, but it is always good to know. Because here we're not talking only about what you will get in the exams, it is about learning the concepts. So, how much is the lambda? You see, it is lower than 1. So we are taking 91% of the CU that we obtained. So CU corrected will be, we are taking 91% of this. 0.91 into what was this, 62.43. How much will that be? Hmm. See, vein shear test we do. Why? To obtain CU value. This is the final outcome of vein shear test. Okay. So anything that we record is to obtain this Cu at the end. It will give us the cohesion value uh, of saturated clays. So we reduce it a bit. You multiply this 0.91 into 62.43. Okay, 56.83. kilonewton per meter square. Okay, so you see from 62 we have reduced it a bit. We have taken only 91% of the CU we obtained from the Wayne shear test for design purposes. So we can write CU design. So as a designer, I will use this value instead of this value in my QU equation. You understand? So that I don't over predict. The I don't 91% is this na that you got from here. This is a factor. 0.91 is equivalent to 91 by 100, which is 91%. Lambda is the factor given by Jerem to reduce this CU from Wayne shear test to design value. This is a factor. It's not a factor of safety, but it is one of the theories. I know you must not have studied this in class, and I said that it is not something that will be asked in the exam, but it is for your own knowledge to broaden your idea about the geotechnical engineering and see how the geotechnical engineering is actually practiced. It is not, we cannot move from book to field directly. There are many things in field that can go haywire, they can go wrong. So we have to make these adjustments. It's just an adjustment. You understand? I think you don't understand that much. That like you have some doubt. Is there a problem? As I said that this is not this has not been given to you in class. This is from my I'm giving this to you from my side. Okay, there are so many things that we can and the purpose of showing this right now was, see, there will be 100 of relations that you can come up with after calculating CU. I have discussed only two just to make you understand that any quantity about the soil's nature that you calculate, you can get many other correlated quantities for that. For example, from CU, you can even get an estimation of the over consolidation ratio of the clay. The relationship, for example, here is given OCR equals beta times Cu field by sigma naught dash. Beta is 1 by 0. 0.055 pi. 64.2. One second. Okay. So can you calculate this? Uh, okay. And OCR is equivalent to 4.175 into, one second. Give me a moment. The Wayne shear test. One second. Please give me a moment. Hmm, I have to actually I'm rechecking the relation because on one source it is written OCR is beta to the power and other is beta multiplied. I'm trying to see which is the hello. Yeah, yeah. Uh, uh, okay, so I'm trying to verify, re-verify the formula for the OCR value because uh, I can see two sources and one of them has written beta raised to the power uh, the Cu by sigma naught and other has written beta multiplied by. I'm just trying to see which is correct. Okay, one second. Just a moment. Okay, so it is 2.175 raised to power 0.972. Okay, so let us just multiply it, not the one of the um, sources was writing it as uh, a raised power, but let us not do that. Into Cu is 64, 62.43, and let's take the pre-consolidation pressure that is given 64.2. So how much will be the OCR value? Okay, so we can say that this is one which is greater than 1. So it's an over consolidated test. Okay, so this was about the first question, and let's move on to the next question. So this is a result of a refraction survey. It's not visible? Okay, let me share my screen again. Okay, can you see it now? Uh, is it okay? Okay, so let's move on to the next question. Okay, so it's a refraction survey at a site in which we have this, let us, distance from source of disturbance and time of first arrival of P waves. Okay, so let us discuss about that a little bit. So we know that what we do in this is if we have a stratified deposit or whatever kind of deposit and we want to know uh, generally about number of strata, we have an energy source here. Usually it is a hammer blow and it results in this shock waves traveling through the strata. So the speed of these seismic waves that are traveling will be different for different strata based on the density, porosity of that strata. Okay, so we have receptors here. So in this table, what you can see is the distance of these receptors. All these receptors that we have, we know the distance from the source of disturbance. This may be from 2.5 meter, we will start 2.5 meter, then the next receptor we have kept at 5 meter, then 7.5 meter, 10, 15, 20, 25. So have we also have these receptors. And at all these receptors, after I have made this energy, have this made this hammer blow, at all these receptors, I I don't calculate, I note the time. See, this is given to me, the distance is given to me. So what I have to note experimentally is the time for the arrival of the first arrival of P wave. So this device can actually capture as soon as the first P wave arrives, it will give you the time of arrival. Okay, so you have the P wave arrived here. Um, am I audible now? Is it okay now? Okay. Please don't hesitate if again you see that my voice is not audible or any problem in seeing my screen or anything. Don't, even if 10 times you have to say, just tell me my voice is not audible. Okay, don't hesitate for that. Okay. So no issue, no issue, please. So as I was saying, did you catch what I was saying about these receptors? Vanita, did you catch what I was saying? Did you get what I was saying about these receptors and the waves? Okay. So at every receptor, you will know the time of arrival of the wave. Okay. So from that data, how do you determine the thickness and the p wave velocity of the strata that are encountered by this soil? Okay. So let us do that. Let me clear this. Okay. So we know that P waves will travel faster than the S waves. Hence, the first arrival of the disturbance of waves will be related to the P wave velocities in various layers. And the velocity of P waves in a medium is given by V equals under root of ES 1 minus mu S over gamma by G 1 minus 2 mu S 1 plus mu S. See, ES is the modulus of elasticity. Of the medium. Gamma is the unit weight of medium. G is the acceleration due to gravity. Mu S is the Poisson's ratio. Okay. So from this, this is the basically principle of our we don't need this right now, but all we need to know is that V is actually related to these properties of the soil. For example, we have a source S, and we have these receptors, and we have two layers. There will be this will be velocity in first layer, velocity in second layer. So here this refraction will take place because this layer will travel. One second, please. One moment, please. Okay. So as I was saying, have you studied this in the class? How to calculate these velocities? Not this, but graphical method of calculation of the velocity and the depth based on this seismic refraction technique. Have you done that in class? So what will happen is that these waves, they will get refracted. Okay, so there will be a refraction angle that we use to study in the light. And this is, for example, V2, this will be V1, this will be V3. So we calculate these times. This will be V1, V2, V1, V1, V2, V3, 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 V2, V1. Do you understand what I'm saying? So there is a method or technique of calculating these velocities and these heights. Have you done this in class, Vanita? Vanita, can you hear me? Am I audible? So have you done this in class? So how do you do that? Hmm. Yes. So we have to draw this slope, and this is the time of arrival. Actually, let us do one thing. Okay. This will be the distance and this will be the time. Let us plot this. Let me plot this in Excel first. Okay. Just then I will copy it because my I'm sharing only the window. Let me plot this in Excel and then I'll paste it on the our PPT. Is that fine? Okay, let me plot this in Excel. I will paste it on the PPT. Okay, so this is done. This is the distance, and this is the time of arrival. Okay, is this visible? Anita, is this visible? Okay, so this is what you will get. As you can see, there are almost three layers. This is one, two, three is not visible. Okay, okay. Let me share again. I think after some time I need to share again and again. Is it visible now? Is it visible now? Okay. So as you can see, there might be almost three layers. This will be one, this will be two, and this will be three, isn't it? So let us calculate. So this slope will give us the inverse of velocity in layer 1. This slope will give us inverse of velocity. Excuse me. Excuse me. Inverse in layer 2, and this will give us the inverse in layer 3. So can you calculate and tell me the values? So Let us say this is A, B, C, and D. So slope of AB will be 1 by V1, which will be equal to this will be x1. Hmm, let's say this is xb, this is xc, this is xd. So this will be xb over tb. Slope of bc will be equal to 1 by v2, which will be equal to xc minus xb over tc, and slope of cd equals 1 by v3 equals xd minus xc dd. So how much is, let me see, so xb is, this is 2.557, 7.5 over, this will be, how much is xc? Oh, this will be tb, tc minus tb, and this will be minus tc. xc is, this is 7.5, 10, 15, 20, 25. 25 minus 7.5 over 27.1 minus 15.24, and this is equivalent to 50 minus 25 over 33.9 minus 27.1. So how much do we get? Vanita, for the slopes? This is 0.49. So our V1 will be 2.032. Uh, okay, but into 10 to power minus 3. Uh, have I written there? Yes. Here we have second into 10 to power. Okay. Let's deal with the 10 to power later. Let's first calculate. Just a second. Hear me? Hello? I hope you can see my screen. Okay, so the second part is 25 minus 7.5 over 27.1 minus 15.24. Vanita, can you hear me? Uh, it is, yes, these are in the straight line. This one, but it is, na? If you can see here, can you see my screen? Here, it is a straight line, more or less. No, no, no. That see, what what you have to do is you have to take the moving average of these, na, these lines. It will be a very small difference because this is how the graph actually looks. The total graph, if we talk about, we make this graph and then we try to identify the different slopes, and it cannot be disjoint. How can it be disjoint? If it is disjoint, which means it means that there is an error in the test. There is maybe there you might have encountered a stone. Yes, this is 7.5 and this is 25. This is 50. This is 25. That is fine, but when you draw a graph, see, Vanita, from the field test, you will never get a straight line. Never. Because there are always experimental errors. There may be some boulders, there may be some rocks in between. It is, you cannot have a straight cut answer. See, this is one slope, this is one slope, and this is one slope. Yes. That means that we have second line and third line is not one line. There is a demarcation here. You see this, can you see how uh, see This is a Excel generated graph of the data given. Okay, can you see two kinks? Can you see that there is a slope here and a different slope here and a different slope here? Can you see that? Is it visible to you? The slope of this line, the slope of this line, the slope of this line. Is it visible to you? This is one slope. This is another slope. This is another slope. Is it visible to you? Vanita, is it visible to you? So don't get caught up in the calculations. Try to see, that is why I always tell you to visualize. Visualize this. If you can actually see with your own eyes that there are three distinct slopes here. Now I am telling you just to calculate the value of these. Don't think about the uh, technique of solving the question that I have to write this coordinate and that coordinate. Don't think about that. Only thing I'm asking is you have drawn the graph between the times of arrival. Now, can you visualize, can you see three distinct slopes? Are there three slopes or two slopes? Are there two slopes or three slopes, Vanita? You can see three slopes. So, can you calculate the value of these three slopes? How can you do that? Okay, so you take these 2 points, you take these 2 points, you will get a moving average kind of thing. Either that or what you do is you calculate the slope for all three intervals and then you average that. But I took this point and this point because when I connect these two, it comes out as a moving average of the other two. That is how we sketch graphs when in class. You remember we get the values and then we interpolate between two values. Okay. So how much is V2? Is your doubt clear, Vanita? I hope uh, it got clear. Huh? See, how do you calculate a slope? You know slope. There are two, three methods. One method is in coordinates where you will have y2 minus y1 divided by x2 minus x1. Yeah. Mm. Also we have, see, also we have when we have a triangle. See, in a triangle we have this theta. When you do tan theta is equivalent to perpendicular by base, isn't it? And then we say if theta is small, we take tan theta as the slope itself. So slope will be perpendicular by base. If I divide it into three triangles, that is what I have done actually. I've divided it into three triangles. Okay. So this was just A1, sorry, XA. This was xb minus xa, and this was xd minus xc. Uh, no, sorry, I'm writing it. This was xb. This was xb minus xc minus xb, and this was xd. This is xc. This is xb. So this was xd minus xc, isn't it? Yeah. Yes. How much? Okay. See how you have to see that. 15 is here and 20 is. I understood what you are saying. Let me show you. See, when I am taking, okay, see, when I am taking 25 and 7, okay, uh, when I'm taking these 2 points, this is, let me forget about it right now, okay? Let me delete this and let me delete this. Let's talk about only the first. See, this is kind of a moving average to the other points. It is the best fit right now. But if I take, how much am I taking? Your 20 and 15 if I take. Okay. So this is the 20 point and this is the 15 point. So this will be my slope, isn't it? This will be my slope. Can you see? See, this will be my slope if I take 20 and 15. Vanita, can you hear me? Okay. So what is happening to these points? They are moving away and away, away and away, isn't it? But if you see the moving average, this will be great. Like the effect of these two will cancel out. You're understanding me? But is this the best fit for this line? Is this representing the line more properly or this? Tell me. Hmm? You're understanding what I'm saying? Uh, okay, okay, no issue, no issue. But you kind of see for yourself. that may be because the values there for the uh, experimental, maybe they will have the same slope, all the values. Maybe I can write my table to give the same slope for points between that, but that does not mean that you will get the same slope in field also. You always have to uh, improvise. Okay. So if you can see for yourself that this is a better fit for this line than this, so you will, your instinct will tell you that this is the line that I should take. Okay. See, engineering is a science of approximation only. It can never be, it can most of the time not be accurate, because in real life things we don't get exactly cut out like what we study in our class. Okay. So, give me the values for these velocities, Vaneta. Okay, let me calculate for this. Okay. Uh, okay. 1 second. Mm, what I have written here is a bit wrong. A bit. 1 second. 1 second. It will be, this will be V1 equals 1 over slope of AB. Okay. So I had written it the opposite way. V2 equals 1 over slope of BC. V3 equals 1 over slope of CD. Okay. So slope from here is, so the velocity V1 from here is, okay, here it is. So these are the velocities in the three profiles. For calculating the depth of these profiles, what we have to do is we have to know these intercepts, that lines I was drawing. We need these intercepts, this, this, and this. So let us say that this is, let's call this Ti1, let's call this Ti2. Okay, so what did we get? Ti1 is 10 and Ti2 is 20. So what you will know, and also this is x. Sorry. So let's calculate the depth of the layers. Let us say that we have three layers. Okay. Let us say this is Z1. Let us say this is Z2. Let us say this is Z3. We have V1 equals 492.13. And we have V2 equals 1. Okay. So we have Z1 will be equivalent to 1 by 2 under root of V2 minus V1 over V2 plus V1. Yes, 10 to power minus 3. Okay. Okay. So let's calculate Z1. How much will be Z1 be? Yes, Vanita, how much will this be? Okay. So calculate from this velocity, na? I've given the velocities, na? Yes, 2.65 meter. So the first layer will be 2.65 meter thick. So for Z2, we have the formula. Give me a moment. So the Z2 is 1 over 2 Ti 2 minus 2 Z1 square root of V3 square minus V1 square over V3 V1 multiplied by V3 V2 over under root of V3 square minus V2 square. Okay. Hmm. This is for Z2. Hmm. For Z2, that will also given by formula. I will give that formula also. Let's find first Z2. Don't forget the 10 to power minus 3 here. Tell me what you get, Vanessa. What did you get for Z2, Vanessa? TI2 here, TI1, TI2, this intercept. I mentioned here that this is 20, this is 10. Okay, time intercept, yes. Z2 comes out to be 8.52 meter. Okay, uh, here there are only two layers. So the third layer is actually going beyond. So here this will be 8.52 meter, and this is going on. There will be no depth for this required because it is here it is a rock deposit and it goes on like bedrock and it goes on uh, below. So there is no depth because the waves are not penetrating it. Okay, so that was the question on that's the question on P waves seismic refraction test. So okay, Vanita, is there any question you want to ask? So this was about the topics covered in week 6. In week 7, you are studying the retaining walls, isn't it? So, is there any question you want to ask? It's okay because see, in the end, it is all only Z2. As I said, here there is no formula for Z3 because, excuse me, you see, because there are only two strata, which means that below the first and the second strata, there is this rock strata that is going on unendingly. You don't need a height for that. If we have only three these na, one, two, three, and this strata is not ending anywhere near. So this is like the bedrock. If we had four different layers, then Z3 we would have calculated. Okay. Any more questions? Okay, Ti2 is this is just as just extend your line to the axis. It is just extension of these straight lines from where we calculated the speeds of